polar coordinate basis vectors. So we have here the point P in 2D, and we've drawn the polar coordinates r and theta, which tell us the location of point P in 2D. And now we want to go further than just the location, and we want to define two basis vectors which are going to be associated with point P. And we're going to call these ER hat and E theta hat, so one for r and one for theta. And the way these are defined is that ER hat is the direction of increasing r, and E theta hat is the direction of increasing theta. So if we think about what those look like on the diagram, if we come here to point P and we think what happens if r increases and theta is held constant, then you see that point P is going to move straight away from the origin, so it's going to move out in this direction, and so that direction is the ER hat direction. And we think about what happens if theta increases. Remember, theta is defined this way, so if theta increases, it gets bigger. So if we see what happens if we increase theta but keep r fixed, right? Then point P here, point P is moving around in a circle like this, right? That's what happens if we just sweep theta around. And so the direction that P starts moving out in, right, is this direction here, tangent to the circle. So that's E theta hat, and it's going to turn out that these two directions are in fact orthogonal to each other. So if we want to figure out the components of ER hat and E theta hat as formulas, then the way we would do that is we would relate them to the regular Cartesian basis vectors I hat and j hat. Right? So let's just redraw those over here. So here is I hat and here is j hat. And if we think about the angles, so the angle theta here, that appears again as that angle. And if you think about the little right angle in here, then you can see that in fact this angle here, that's also going to be theta. All right, so let's just redraw this a bit bigger down here. So here is I hat and j hat. And we've got ER hat, so ER hat is a vector that looks like this. Whoops, that's the wrong one. ER hat is like this. This angle is theta. The length of this is 1. In fact, everything's length 1 because they're all unit vectors, as we see from the hats. So we want to figure out the components of ER hat. We draw the little perpendicular line here, and we see here that this distance is cosine theta, and that distance is sine theta. And so if we just write out the two components, we see that ER hat is equal to cosine theta in the I hat direction plus sine theta in the j hat direction. Now similarly, we can come over here and we can look at E theta hat, where now this angle is theta, and again we draw our perpendicular line, and now the vertical distance here is cosine theta and the horizontal distance is sine theta. But if you think about the horizontal distance, it's in the opposite direction to I, so that's negative sine theta I hat plus cosine theta j hat. Let me just do a little quick exercise here. We can just check that in fact ER hat and E theta hat are right angles to each other. And the way we do that, we want to check that two things are at right angles. We take their dot product. So here we multiply together their I hat components, cosine times sine with a negative sign, so negative cos theta sine theta, plus the multiplication of their j hat components, so plus sine theta cosine theta, and these obviously cancel, so that really is 0, and we see that these guys really are at right angles, just like we said they were going to be. All right, so let's just do one little quick example here. So let's suppose that we're told that in fact E theta hat is a vector that looks like this, pointing downwards and to the right at about a negative 45-degree angle. And the question is, well, where is point P in 2D? Right? So P is somewhere on the xy axes, but where is it? So let's just think for a second. Maybe point P would be out here, right? So point P here. But if we think about this, well, in fact, ER hat would be that way, and E theta hat is this way, right? So that certainly is not where point P is. If point P moves around, suppose it moves around out to here, Well, at this stage, right, so remember theta was like this, and then we increased theta around even further, and we still just chose some r here. So now if we were to increase theta yet further from this point P, then e theta hat would be pointing this way, also in the wrong direction. If we continue to increase theta even more, right, so we sweep point P around even further, well, we can see now if we were to increase theta further here, then in fact point P is moving this way, and so in fact this actually is where point P has to be if e theta is pointing downwards and to the right. So now let's just think about r for a second. So what would happen if we chose a different r? Suppose we come out here, and in fact now point P is out here. We have this really long r. Theta is still exactly the same kind of value. Well, if we increase theta, well, e theta hat is still pointing down and to the right because that's still the direction that point P would be moving. And the length of e theta hat won't be any different because in fact in both cases it's a unit vector because it's got hat on it. It always has length 1. So in this case here we see that the answer is that P is in the third quadrant, and in fact basically theta is something like 225 degrees, right, roughly speaking, depending on exactly what angle that is. But we don't know anything, so we don't know exactly what the radius is, how far away from the origin we are. E theta hat doesn't tell us anything about that.